Hi there. This video is about calculating the heat needed to get through the change in state of matter. There's really two parts of this, and we're going to be looking today in this video is really this upper part. I can explain what's happening to the molecules. What are they actually doing to go through state of matter change? State of matter change is going from a solid to a liquid to a gas. And we've covered the terms for these like melting and freezing and boiling, but there's new words in this chapter. The chem gods love to do that. Your new word from solid to liquid, normally you'd think melting, but in this chapter it's called fusion. Same thing, different word for the same thing. But liquid to solid is called solidification instead of freezing. Kind of makes sense. Liquid to gas, we're looking at vaporization. And a gas to liquid, we're looking at condensation. So these are four new terms to know. Hopefully you've got your notes out and you're adding the notes as we go. At any time if I go too fast, certainly hit pause or rewind or whatever you might need to do. Now this chapter is going to be looking at how much heat does it take to fuse or melt a substance, or how much heat does you have to remove to solidify or freeze a substance. And that brings us to another new term, this change in H thing. Notice it has the FUS. That would mean it's the molar heat of fusion. Molar heat of fusion is defined as the amount of heat needed to melt or fuse 1 mole of a substance. Now you can actually have terms for all four of these spots. Notice the symbols are pretty much the same. The only thing you're changing is changing one of these red words, solidification or vaporization or condensation. So if we kind of put it all together, it's really the same definition just 4 times. Molar heat of fusion, we already covered, the amount of heat needed to melt 1 mole of a substance. Or the vaporization, amount of heat needed to vaporize 1 mole of a substance. So molar would assume that you have 1 mole, and all these definitions deal on 1 mole. And then it's just how much heat you need to get through a different state of matter change. That brings us to this part. In this chart, we're taking a look at heat, or how much energy or heat you need, based on a certain temperature. So if you start at the beginning of time at a really cold temperature where no heat is added, you're as a solid down here at the bottom. As we slowly add heat, we start to increase our temperature and things start to move faster. And anytime our temperature is changing, that means the molecules are moving faster or slower. So as we increase the temperature of a solid, we get it to move faster until we hit this spot right here. At this point, we start to melt. And if you look, from this point all the way to this point, your temperature has not changed. It has stayed the same the entire time. Which means if you have a glass of ice water, and it has 1 ice cube in it, and it's fully stirred, it'll be 0 degrees Celsius. If you have a glass of ice water that has 5 ice cubes in it, it'll still be at 0 degrees Celsius. It doesn't matter how many ice cubes there are, when you're melting and freezing, it must stay at the same temperature, 0 degrees Celsius. But you're still inputting heat, so the question is, what's happening during that heat change? And that's what this whole lecture or video is about. Let's look at the numbers first. Numbers are sometimes easier. So if you want to go from a solid to a liquid, and that's what we're talking about melting, it's going to take a certain amount of energy, which is 6.02 kilojoules per mole. To get through the heat of fusion, you need to add 6.02 kilojoules if you have 1 mole of ice. If you wanted to go to backwards, this is going from liquid to solid, you can see it is the same number, the only thing is it's negative, because we have to remove energy in order to solidify or freeze something. You might be thinking, I've seen this H before, and you have. You totally have. That's right here in the mole map, where we can see how much heat it takes. That's in balanced equations, but here I have a balanced equation too. Solid to a liquid, it's a really simple one, but we still have that H value in there. So let's do a practice problem with that. Let's get to the practice problem after this. Sorry about that. First, let's talk about what's actually happening when something goes from a solid to a liquid. If we're actually inputting energy, but the temperature doesn't change, then what's actually happening? Here's your solid ice, and it's forming a liquid water. So in a solid state, you can see that one water molecule and another water molecule are directly next to each other. They're intermolecularly attracted to each other. And these big, long white parts here, white bonds, are showing the intermolecular hydrogen bonds. They're intermolecularly attracted. Now if you look over at the liquid part, they still are intermolecularly attracted to each other, but not as much. It's not a set structure. As a solid, this water is next to this water, and they're stuck together. But as a liquid, they kind of move past each other. So the intermolecular attraction that holds these two waters has to kind of break down for a moment, or loosen. To go from a solid to a liquid, you have to loosen your intermolecular attractions. I write that down. To go from a solid to a liquid, you have to loosen your intermolecular attractions. All of the energy that goes to melting ice goes to breaking down those intermolecular attractions, loosening the IMFs. Let's go back to the mole map. So to loosen the IMFs, it'll take 6.02 kilojoules per mole. But let's say you happen to have 78 grams of ice. And you want to know how much heat will it take to melt 78 grams of ice. Seems to me this brings me back to stoichiometry, where I say to myself, question mark kilojoules is equal to 78 grams of water. From here, it's just a stoich problem. So if you want to pause it and try it yourself, go for it, but I'll help you through it. So if I've got grams on top, I've got to put grams on bottom. And I'm going to go to moles first. That's because this number here is per mole. I know how much energy it takes to do 1 mole of ice, but I don't know how much it takes to do 78 grams of water. So let's go from grams to moles first. If we go to grams to moles, the periodic table is the thing that I need. So I'll look up on the periodic table. Periodic table says 1 mole is equal to 18.0148 grams of water. That 18.0148 is the molar mass of water. That's the periodic table number. So now my grands cancel, grands on bottom, grands on top. I'm left with moles on top, so I've got to have another fraction because I'm trying to get to kilojoules. So I've got to have moles on bottom of my next fraction, and I do. Moles on the top and moles on the bottom will cancel. I got kilojoules on top now, and that's where I want to go. Thinking about these numbers, I can see in the balanced equation, or the molar heat of fusion tells me per mole, per 1 mole, I need 6.02 kilojoules. That 6.02 is going to go right there. Now I wanted to get to kilojoules, and I'm in kilojoules, so I just got to push buttons in my calculator to finally get the number. I got 26.1. Considering though I only have 2 sig figs here, I should really say 26 kilojoules. So that's how we can use the mole map, knowing that H, or molar heat of fusion in this chapter, is right here. Let's look at our next state of matter change. Here we're looking at how much energy does it take to go from a liquid to a gas. A liquid to a gas. To do that, you need a lot more energy, actually, 40.6 kilojoules per mole. What if you wanted to do the exact opposite? What if you wanted to go from a gas to a liquid? That's the opposite. It would take the same amount of energy, 40.6, except you'd have to remove 40.6 kilojoules per mole, so it's a negative value. We've got to make it colder, so I've got to take out heat, 40.6 kilojoules, to remove that. Well, let's think about what happens if you're liquid water, here's liquid water, and you want to become a gas. As liquid water, the waters are sliding past each other. So they're intermolecularly attracted to this water for a little bit, and then intermolecularly attracted to this water for a little bit. They've got attractions, and they kind of slide past each other. As a gas, if you remember the gas chapter, gases aren't attracted to anything. Gases are not attracted nor repelled by any other gas around them. So they have no intermolecular forces. There are no intermolecular forces as a gas. To go from a liquid to a gas, you have to entirely break the intermolecular attractions. All of the energy goes to breaking intermolecular attractions to become a liquid to a gas. Here's your next problem. It looks just like the other one. This time we have 243.1 grams of water, and you're trying to remove or add amount of heat to condense that water. So try it just like the other mole map. Ask yourself question mark kilojoules equals, in this case, 243.1 grams of water. You're going to take it from here. Try this problem in your notes, and I'm asking you for your answer to this problem in the Google form. So next is you're going to go to the Google form, and I'm going to ask you some questions. I want you to seriously reflect on what you learned in this video and do the best you can on the answers, and ask me any questions that you might need. I'll see you next time.